let's start with matrix factorization because we want to study factorization based method. So let's understand what is matrix factorization. You must have studied matrix factorization in your linear algebra class or any class or course on introduction to machine learning in terms of dimensionality reduction techniques. For example, you must have studied principal component analysis or non-negative matrix factorization or semi-negative matrix factorizations. They are examples of matrix factorization techniques. Unlike decompositions which we study like LU decomposition or QR decomposition in linear algebra, the matrix factorization objective is to decompose a matrix into a lower dimensional latent space. So here we take matrix A and which is of dimension m cross n. We are going to decompose it into U and V transpose, where U is m cross D and V is n cross D. Here D is quite smaller than m and m. So it is the dimension m and n are quite larger compared to the D. Hence we get a lower dimensional representation or decomposition of our matrix. And to achieve this particular task, what we do, we minimize this objective function, or in other words, we try to represent a matrix as a set of constituent part. You can think of this as a constituent part of using U and V transpose. So here, as I told you, we are minimizing Frobenius norm square to find out this decomposer U and V. Here U and V are of lower dimensional space. So this is what is a matrix factorization. To perform the matrix factorization, we need to learn something called singular value decomposition. It is an algorithm which factorizes the matrix into three matrices U, D and V transpose. Here U is m cross m matrix containing the orthonormal eigenvectors of AA transpose. V is n cross n matrix containing the orthonormal eigenvector of A transpose A, and D is a matrix of dimension m cross n containing the singular value of AA transpose. And what we can do here is we can examine U, D and V transpose. Particularly we can examine D to figure out what is lower dimensional space. So how we can do that? So let's look at A. So let's say A is m cross n. When we decompose it, we have U m cross m D, which is again this is U, this is D, which is m cross n, and this will be similarly n cross n. This is D and this is V transpose. Now, as we discussed that D is AA transpose eigenvalues or singular values. Hence, if you look at it, the first m values, and particularly it has a diagonal we can values here, and remaining will be 0 here. So here we can examine the singular value of in the D, which has some value. This will be lambda 1, 2, up to lambda m, and we can examine this singular values and find out which are very close to 0 or near to 0. The near to 0 eigenvalues, if you look at it, will leads to a decomposition of this matrix into two parts. You can see U1, D1, V1 transpose plus U2. So I can divide them, U2 D2 V2 transpose. Here D2 contains eigen singular values equal to 0, hence this term will be equal to 0, only this term I am saying, and resultant we have U1 D1 V1 transpose, or we have U tilde V tilde V transpose, V1 transpose, this is tilde, and this will be of dimension, let's say there are P non-zero eigenvalues, then we have or D non-zero eigenvalues or singular values, so we have M cross D here and D cross N here, and this way we get a lower dimensional space using singular value decomposition by just examining the singular value in the D. Okay, so we'll use this particular aspect when we talk about the factorization based embedding. Now let's look at the factorization based embedding approaches. As I told you, it's a method based on the matrix factorization. Here idea is to decode a local neighborhood structure from the node embedding, such as entries of the adjacence matrix. The objective here is to perform the factorization to learn a lower dimensional approximation of a node-node similarity matrix S. So I'll create a similarity matrix S, which can be adjacency matrix, that's one simple way, and use a matrix factorization to perform a lower dimensional approximation. Typically S generalize the adjacency matrix and is try to capture the useful information about the nodes in the graph. The first factorization method that we are going to look at is inner product method. In the inner product method, we are first going to look at graph factorizations, which is similar to matrix factorizations. What is the objective of graph factorization? The objective of the graph factorization is to find latent factors associated with nodes of a graph G, V and E. V is node set, E is an edge set. Using this particular graph G, I can define adjacency matrix A, which is n cross n dimensional matrix, and it is a symmetric matrix. Now the objective here is to find Z, which is belongs to n cross R, where R is lower dimension, it is very lower than n, which is number of nodes, such that Z transpose is approximately equal to A. Here we are defining inner product between Z and Z transpose, and that's why it is inner product based method, and we will look at that when we that how inner product is defined for each node pairs. Let's take a simple example here. U and V belongs to V, which is any pairs of the node in a V, and corresponding node we have an element in my adjacency matrix, which is I have called AUV. And what we are interested in is that we want to compute or find latent factors or embedding such that the inner product between the embedding of U and embedding of V is approximately equal to A of UV. Then what is the loss function we are actually minimizing? So here my loss function is for each pair of nodes in V, or each pair of edge and E, I want to find out embedding such that is minimizes sum square of all the elements in my adjacent matrix. Okay. So this is a very simplistic point of view of performing graph factorization, or we can think of that if you look at the A here, what I am trying to figure it out how can I perform Z by Z Z into Z transpose, which is factorization of A into two matrices such that my n cross n is equal to n cross r and r cross n. And here this one will give me the desired embedding. Okay. So I can take this embedding and define the F embedding function, decoder functions, etc. Here this is my L. If you think of, this is my L, this is my decoder function, this is my similarity function between two nodes function, and this is a form of my my L, and this provide my loss function. Now there is another method called GraRep. The objective of this particular method is to find a latent factor associated with the nodes of a graph by incorporating global graph structure information. So far we looked at the just adjacency matrix in a graph factorization. Now this particular researchers says that can we actually extend the same idea to incorporate global graph structure information instead of neighboring relationships between nodes. Here idea is to incorporate global structure information of a graph such that a relationship between two nodes at long distance can be also keep into the account, as well as age weights also can be keep into account. So sometime in certain graphs there is a different age weights, and that actually we would like to incorporate in our matrix factorization method or in embedding method. So here what we are getting is, or what we are trying to do is, in some way we are trying to use scaled adjacency matrix. So this scaling can be anything. So AS is some kind of M into A, where M is some scaling matrix. Sometimes people denote it as an inverse, but we will keep what we mean is that we are multiplying M to the adjacency matrix. M is a scaling matrix and got a scaled adjacency matrix. And in graph representation, what we are interested in is figuring out latent embedding Z belongs to n cross R is less than or equal to n, such that it is approximately equal to the scaled adjacency matrix. And the loss function again is going to be similar. We are going to use the inner product between embedding between ZU and V and the element of the scaled adjacency matrix, and we will try to minimize the sum over all the possible combination in A. The third approach people have used is inner product based method, is called HOPE or HOPE, HOPE, higher order proximity preserved embedding. Here the idea or the main motivation here is, can we actually preserve asymmetric relationships? For example, in a directed graph, if I have a directed graph, let's take a simple example of 3 nodes. I have a U, V and W, and I have a directed graph from here to here, here to here. Now, if you look at the neighboring relationship, there is a direction from V to W to V, but there is no direction from W to U. However, if I do not do this way, I just keep it as an undirected graph like earlier we have constructed throughout this particular example, then in this case I can apply any other methods which we have used earlier. However, just by adding arrow, I cannot use some of this method. So idea here is to actually use some higher order proximity measures which allows us to actually preserve asymmetric transitivity in the directed graphs or some other asymmetric transitivity which cannot be preserved using some of the methods we have seen earlier. So they use some of the higher order proximity measures such as cards index, common neighbors, Adamic adder or page rankers kind of indexes to find out the latent factors associated with the nodes of the graph. So here we are going to define a high order proximity matrix APM, which is proximity matrix, which is again R cross N cross R in R N cross N symmetric matrix. Here the objective is to find ZS, which is source embedding and target embedding. Remember that we cannot get certain embeddings because of this asymmetric transitivity in the directed graphs, and we want to find out, can we actually have this lower dimensional representation which allows us to decompose APM in ZS and ZT transpose. Again, the problem formulation point of view, we have to find appropriate higher order proximity matrix of G. After that, the method of factorization remains same. So loss function is again minimization of Frobenius norm between these two. You can go to this particular article and see what different kind of proximity measures have been used and their forms, but the idea remains the same. Hence, in inner product based methods, we can actually conclude that the decoder embedding are based on the inner product of embeddings, where decoder of any two nodes function is basically takes embedding of ZU, ZV of the form of ZU transpose ZV, which is basically inner product between two vectors. And that's the most common element between all the three methods which we have seen in the last couple of minutes. The assumptions here is the similarity between the two nodes is proportional to the dot product of their embedding. Okay. And that similarity here comes in a different form, adjacency matrix or scaled adjacency matrix or some higher order proximity metric which or measure which allows us to represent two nodes similarity in terms of n cross n dimensional matrix. So here the S is keep changing. However, the embedding or decoder function is not changing. Here, similarity functions, as I told you, can range from adjacency matrix to the more generalized approaches such as the power of adjacency matrix, neighborhood overlapping measures, or even function of adjacency matrix, polynomial function of adjacency matrix. So this is inner product based method.